Right now, you are hurtling through space at over 1.9 million miles per hour. You feel nothing. That silence is the lie. Earth does not just orbit, it spirals, falls, and gets dragged towards something so massive we spent 30 years looking in the wrong place. Behind us, a billion light-year void pushes. Ahead, a supercluster of tens of thousands of galaxies pulls harder, and buried inside a fossilized sound wave from the Big Bang sits a ring that should not exist. We will visit the hidden attractor, the void that drives us forward, and the fate the universe may have already decided. If you want to see where this goes, subscribe. We begin. Right now, you cannot feel it. The surface beneath you is solid and still. The air in the room holds its shape. Your hands rest where you place them. Everything confirms the same quiet story. You are at rest. The ground beneath you is moving at over 1,000 miles per hour. At the equator, Earth's surface rotates at approximately 1,040 miles per hour. That is faster than most commercial aircraft. Fast enough to carry you around the entire circumference of the planet in just under 24 hours without ever leaving the surface. Fast enough that if you could somehow step off the planet and watch from a fixed point in space, you would see the ground blurring beneath you. And yet, standing on that ground, you feel nothing at all. No wind, no vibration, no force pressing sideways into you, just stillness. The reason is precise, and it matters for everything that follows. When every part of a system moves at the same speed and in the same direction, no part of it can detect the motion internally. The air, the ground, your chair, your body are all rotating together at identical speed. Physics calls this an inertial frame. A passenger on a smooth flight at cruising altitude feels no sensation of speed because nothing inside the aircraft is shifting relative to anything else. Motion only becomes perceptible when something in your environment is changing speed or direction relative to you. For a spinning planet, that contrast never happens. The whole world turns with you, and so the spin is invisible. Here is where the strangeness begins to build. Earth does not only spin, it also moves through space around our star. The entire solar system carries itself through the arms of the galaxy at speeds that make Earth's rotation look gentle. And the galaxy pulls through something larger still, aimed at a destination that took humanity most of its scientific history to even begin to identify. These motions do not cancel each other out. They stack. Each layer sits on top of the last. Each one is faster, stranger, and harder to explain than the one beneath it. This story is the full accounting of those layers. Some of what scientists found along the way was clean and satisfying. Measurements confirmed, velocities matched predictions, the mathematics behaved, but other layers overturned decades of confident calculations. One major discovery turned out to be catastrophically wrong within 20 years. Another revealed that the object believed to be pulling us through space was, in fact, barely a fraction of the real cause. And the deepest layer of all remains contested, its implications so radical that even the scientists who found the evidence are still arguing about what it means. Each chapter ahead adds one more layer to the picture. Each one makes the previous look small. The rotation is the starting point, 1,000 miles per hour, invisible to every human who has ever lived on this surface. An enormous speed that registers in your body as nothing at all. It gives us day and night. It shaped every civilization that ever organized itself around a calendar. It is the motion most baked into human experience. And in the full accounting of Earth's true speed through the cosmos, it is almost negligible. The total velocity, confirmed by direct measurement against the oldest light in the universe, exceeds 1.9 million miles per hour. The destination that all of that speed points toward took scientists until the late 20th century to begin to map, and they are still revising the answer today. We begin at the slowest point. This is the slowest we will ever move in this story. For most of human history, the idea that Earth moves at all was considered absurd. The ground felt permanent. The sky wheeled overhead. Every everyday observation pointed to a stationary Earth and a moving cosmos. It took centuries of astronomy, philosophy, and contested mathematics to establish the opposite, and even then, the motion remained something to be argued in books rather than felt in the body. The facts, once established, are staggering. Earth orbits our star at approximately 67,000 miles per hour. That is the equivalent of traveling from one side of the continental United States to the other in about 3 minutes. In a single day, Earth covers more than 1.5 million miles along its orbital path. In a year, it sweeps through nearly 600 million miles, returning to almost exactly the position it started, and doing it so smoothly that the ride is undetectable. The silence of that journey is what makes it so disorienting to think about. There is no air in space to push against the planet, no friction, no medium, no resistance of any kind. The planet travels through near-perfect vacuum, and vacuum offers no sensory feedback. On Earth, speed communicates itself through wind, through vibration, through the compression of air. Remove all of that, and speed becomes invisible. The most extreme velocities in the solar neighborhood pass without any signal to the creatures riding them. That invisibility is why the heliocentric model of the solar system was so difficult for early scientists to establish. The correct picture, that Earth moves around our star rather than the reverse, was proposed in ancient times and suppressed, then proposed again, and fought over for generations. The problem was not just religious resistance. It was genuinely hard to understand how a moving planet could feel exactly like a stationary one. That puzzle has a real answer, the same inertial frame that explains the rotation, but it required a complete rethinking of what motion means. Here is something worth sitting with for a moment. Earth has been traveling at 67,000 miles per hour, without pause, for 4.5 billion years. That motion has never slowed, never varied significantly, never been interrupted. Every person who ever lived, every civilization that rose and fell, every species that walked or swam or crawled across this surface did so while the ground beneath them was already deep into this journey. The journey predates life itself by hundreds of millions of years, and this orbital motion, vast and ancient as it is, does not explain our full speed. The solar system and the star it orbits are not fixed in space. They are themselves in motion through something larger, carried along by forces that dwarf the simple orbital mechanics of one planet around one star. The 600 million miles Earth traces each year is itself a tiny arc inside a much grander trajectory that takes the solar system on a journey no single human lifetime could meaningfully measure. When early astronomers concluded that Earth circles our star, they felt they had found the real answer, the fundamental truth about our motion. It was a brilliant achievement that restructured all of science. It was the second layer of a much deeper story. What sits above it makes 67,000 miles per hour look like the calm before a storm. Imagine a clock so large that 1 second on its face equals 1,000 human lifetimes. Imagine one full rotation taking so long that the last time its hand was in its current position, reptiles had only recently begun their domination of the land. That is roughly the scale of the orbit you are currently completing. Our solar system circles the center of the Milky Way at nearly 500,000 miles per hour. That figure is confirmed through multiple independent measurements. The orbital speed varies slightly depending on the method used, but the range settles around 496,000 to 560,000 miles per hour, roughly 220 to 250 kilometers per second. By any comparison to anything in ordinary human experience, that speed is incomprehensible. Yet the orbit is so enormous that even at that velocity, one full trip takes between 220 and 250 million years. Astronomers have a name for this. One orbit of our solar system around the galactic center is called a cosmic year, or a galactic year. The last time Earth occupied its current position in the galaxy, the Triassic period had not yet begun. The first true dinosaurs were just appearing on a planet whose continents looked nothing like today's. Before that orbit, there were no dinosaurs at all. Before the one prior, there were no terrestrial vertebrates. Travel back through 20 of these orbits and you reach the formation of Earth itself. That is how many cosmic years our planet has completed in its entire existence. 20. 20 complete laps around the galaxy. That is the full history of this world. Think about what that means for scale. The Milky Way is so large and the orbital path so immense that even a planet as old as Earth has barely begun to explore the galaxy it lives in. And our galaxy is one of hundreds of billions. Now here is where this chapter needs to build towards something larger, because 500,000 miles per hour, the speed of our galactic orbit, confirmed and measured and written into textbooks, is itself only one layer. The solar system is not simply drifting in a quiet circle at the edge of the galaxy. The entire galaxy and everything near it is moving, coherently, in a specific direction, at a speed that, layered on top of everything else, produces a combined velocity that no one in the history of science suspected until fairly recently. The Milky Way sits in one of the galaxy's minor spiral arms, roughly halfway between the galactic center and the outer edge. Our position is neither central nor peripheral in the extreme. We are riding mid-orbit in a structure that contains at least 200 billion stars, all of them also orbiting, all of them also in motion. The neighborhood around us shifts over cosmic time. Stars that are close today will be distant neighbors in 10 million years. Constellations that define our current sky will look entirely different after another cosmic year. By the time we have added the final layer, the comfortable orbital motion you are currently completing around the galactic center will seem almost leisurely. To understand what comes next, you need to understand how scientists first noticed something was wrong. It was not a grand telescope discovery. It was not an obvious signal. It was a subtle pattern in numbers that should not have been there. And the 7 astronomers who found it had no idea, at the time, how deep the rabbit hole went. They only knew that galaxies were moving in a way that could not be explained. Something was pulling them. In the mid-1980s, a group of 7 astronomers began accumulating data that did not fit. They were studying elliptical galaxies, measuring distances using a technique called the fundamental plane method, which relates the size and brightness of a galaxy to its internal velocity. It was meticulous, painstaking work, and the numbers kept coming back wrong. The team called themselves the 7 Samurai, a name that captured both the size of the group and, perhaps, the sense that they were fighting against something large and uncertain. They were David Burstein, Roger Davies, Alan Dressler, Sandra Faber, Donald Lynden Bell, Roberto Turlevich, and Gary Wegner. Their joint work, published formally in 1987, documented something extraordinary. Galaxies across a huge swath of the sky were moving hundreds of kilometers per second faster than the standard model of cosmic expansion predicted. To understand why this was alarming, you need to understand what peculiar velocity means. When astronomers measure how fast a galaxy is moving away from us, they expect to find a number governed by Hubble's law. In a uniformly expanding universe, every galaxy recedes at a rate proportional to its distance. The further away it is, the faster it moves away. But sometimes, a galaxy is moving at a speed slightly different from that prediction. That difference, that deviation from the expected expansion rate, is called peculiar velocity. It means something nearby is exerting an additional gravitational pull on the galaxy, nudging it faster or slower than pure expansion would produce. What the 7 Samurai found was not a small nudge. It was a systematic, coherent drift across thousands of galaxies in a vast region of sky, all streaming in the same direction, all showing the same deviation. The pattern was too consistent, too large, and too organized to be noise. Something was pulling them all. The pull was aimed at a region in the direction of the constellation Centaurus. The galaxies were not just expanding away from each other the way a uniform universe would produce. They were also sliding sideways, pulled toward a single point in the sky. That point corresponded to a region of enormous mass, mass so concentrated that it was accelerating everything in the neighborhood toward it. Alan Dressler gave it a name. He later said the object needed something more evocative than a dry technical label like New Supergalactic Center or Very Massive Object. The name he chose was simple, accurate, and slightly ominous. He called it the Great Attractor. The name stuck because it captured the thing itself. Something out there was attracting matter on a cosmic scale. Galaxies hundreds of millions of light years away were being drawn toward a single concentration. Our galaxy was among them. Our solar system, our planet, everyone, and everything on it was moving toward the Great Attractor, had been moving toward it for billions of years, and would continue doing so indefinitely. The natural next question was, what was it? That question turned out to have a deeply frustrating answer, because the Great Attractor was sitting in exactly the wrong place in the sky. There is a quarter of the sky that optical telescopes cannot see. It is not dark. It is not empty. It is, in fact, one of the brightest regions of the night sky, thick with stars, glowing gas clouds, and dense lanes of interstellar dust. That brightness is precisely the problem. The disk of our own galaxy runs through the middle of this region like a band of fire, and everything behind it is hidden. Light from distant galaxies passing through that band is absorbed, scattered, and overwhelmed by the foreground. Billions of stars between us and the objects we are trying to study make them effectively invisible. Astronomers call this the zone of avoidance. It covers approximately 1/4 of the entire celestial sphere. Any survey of the universe that relies on optical light simply has a gap there, like trying to map a continent with 1/4 of your map torn away. For most of the history of modern astronomy, that gap was accepted as an unfortunate limitation. You worked around it. You filled in what you could and left the rest blank. The problem with the Great Attractor was that it sat almost directly behind this zone. The mass concentration that was pulling our galaxy, our neighborhood, and hundreds of thousands of other galaxies through space was hidden behind the single most obscured region of the sky available to us. The irony was not lost on the scientists trying to study it. They had identified its gravitational signature in the motions of galaxies on both sides of the zone. They could see its influence the way you can see the effect of a current in a river without seeing the current itself. But direct observation was blocked. The veil refused to lift. To penetrate the zone of avoidance, astronomers had to abandon visible light entirely. Radio waves pass through interstellar dust with much less interference than optical photons. Infrared light is similarly more penetrating. X-rays, generated by the hot gas in massive galaxy clusters, can punch through even dense regions of the galactic plane with reasonable clarity. Over the following years, after the Seven Samurais discovery, teams of astronomers worked through all of these wavelengths, trying to map what lay behind the obstruction, trying to finally see the thing that was pulling them. The picture that emerged was not clear at first. Different surveys produced different results. Different estimates of the mass gave wildly different numbers. The identity of the core object behind the Great Attractor, the specific structure at its heart, took years to nail down. And when it was finally identified through X-ray observations, the result was genuinely impressive. Thousands of galaxies locked in gravitational embrace, collisions on a scale that defied ordinary description, energy output that registered across the electromagnetic spectrum. But something was already going wrong with the numbers. The mass estimates were off, and the scale of that error would not become fully clear for another decade. What scientists thought they were looking at, what the early data suggested they had finally pinned down, was about to reveal itself as a partial answer at best. When the full picture arrived, it required rewriting almost everything that had been published in the 20 years since the Seven Samurais' original discovery. The breakthrough came from orbit. The Roentgen satellite, launched in 1990 and known as ROSAT, was designed to survey the sky in X-ray wavelengths. Hot gas trapped in the gravitational wells of massive galaxy clusters radiates intensely in X-rays, and X-ray light is less impeded by the dust and gas of the galactic plane than optical light. It was not a perfect solution to the zone of avoidance problem, but it was a way in. In the early 1990s, X-ray observations from Rosat revealed the dominant structure behind the Great Attractor Zone. It was a galaxy cluster, catalogued as Abell 3627, but better known by the name of the constellation in whose direction it sits, the Norma Cluster. What the data showed was impressive by any measure. The Norma Cluster contains thousands of galaxies in a region of space far smaller than they should comfortably occupy. Many of those galaxies are colliding, caught in the slow gravitational crush of neighboring masses too large to avoid. The collisions produce enormous quantities of radio waves. The hot gas permeating the cluster glows in X-rays. The whole structure is a seething, radiating knot of matter in a gravitational embrace that has been tightening for billions of years. It had mass, enormous mass, and the early calculations suggested a figure that seemed to justify everything the Seven Samurai had found. Early estimates placed the total mass of the Great Attractor region, with the Norma Cluster at its core, at roughly 10,000 times the mass of our neighboring Andromeda galaxy. Andromeda is a system of approximately 1 trillion stars. 10,000 times that is a number almost beyond useful human visualization. If those estimates were correct, the Great Attractor was among the most massive concentrations of matter in the local universe, and its gravitational influence on everything in the neighborhood, including our own galaxy, was fully consistent with the peculiar velocities the Seven Samurai had measured. For roughly a decade, this was the accepted picture. The Great Attractor had been located, its mass estimated, its identity confirmed. The anomaly in galaxy motion had an explanation. The case was effectively closed, except the numbers were wrong, not slightly wrong, not marginally off in a way that required a small correction. The mass estimates would eventually be revised downward by a factor of 10. The object identified as the primary driver of our galaxy's motion across space would turn out to account for less than half of that motion. And the real dominant attractor, the structure genuinely responsible for the largest part of our trajectory through the cosmos, was not in the Great Attractor Zone at all. It was 4 times farther away, in a different part of the sky, and had been noticed decades earlier by a different astronomer entirely. That astronomer had no idea what he was looking at in 1930. Neither would anyone else for another 70 years. Science does not always correct itself quickly. The mass estimates for the Great Attractor were accepted, published, cited, and built upon for approximately 2 decades. Research teams used those figures as the foundation for models of galaxy flow in the local universe. Papers calculating peculiar velocities, mapping the gravitational landscape, and tracing our cosmic trajectory all rested on numbers that were, it would turn out, dramatically inflated. The correction came in 2005 from a survey called the Clusters in the Zone of Avoidance project. This X-ray survey, designed specifically to map galaxy clusters hidden behind the galactic plane, produced revised measurements of the Norma Cluster and the surrounding region. The new figures were startling. The Great Attractor region was only about 1/10 the mass originally calculated, not 1/10 of a few percent less. 1/10. The early estimates had been off by a factor of 10. And the reason was a statistical artifact called the Malmquist bias. Understanding the Malmquist bias requires grasping one particular problem of cosmic observation. When you survey the sky for galaxy clusters, the clusters you can detect are the brightest and most luminous ones. Clusters that are less bright, less massive, and therefore harder to see get undercounted. The survey does not capture a fair sample of everything out there. It captures a sample weighted toward the large and the bright. When you then calculate the mass of a region based on the clusters you can detect, you are systematically inflating the estimate because you are missing all the smaller ones. The early estimates of the Great Attractor's mass had suffered exactly this distortion. The Norma Cluster and its neighbors were massive, confirmed, and real. But the surrounding region was nowhere near as packed with matter as the early calculations assumed. Strip away the Malmquist bias, and the number collapsed. Here is the consequence that mattered most. The peculiar velocity of our galaxy, the speed at which the Milky Way is moving toward the Great Attractor region, above and beyond simple cosmic expansion, requires a specific amount of gravitational pull to explain it. The revised mass of the Great Attractor could only account for approximately 44% of that velocity. The rest needed an explanation. Something else was contributing to the pull, something larger, something farther out, something that the 30 years of research focused on the Great Attractor had not adequately addressed. The cosmic mystery that the Seven Samurai had uncovered in the 1980s had not been solved. It had been partially explained by a structure that turned out to be a supporting actor in a story with a much larger lead. That lead had been sitting in plain sight since 1930. Harlow Shapley had noticed something unusual in that direction of the sky nearly a century earlier. He called it a cloud of galaxies, which was modest understatement. What he had found was the most massive concentration of galaxies in the local universe, and almost no one had taken it seriously enough as the dominant attractor. That was about to change. Harlow Shapley was one of the most important astronomers of the 20th century. He was the person who correctly placed our solar system in the outer regions of the Milky Way, overturning the assumption that we occupied a central position in the galaxy. His insight permanently changed how humanity understood its own location in the cosmos. In 1930, in the course of his broader surveys of the sky, Shapley noticed something in the constellation Centaurus. A concentration of galaxies that seemed unusually dense, more packed together than the surrounding sky. A region where the census of galactic objects was markedly higher than average. He noted it, he published it, and for decades, the astronomical community largely filed it away as an interesting observation without pursuing its full implications. The Shapley concentration, as it came to be known, sits approximately 650 million light-years from the Milky Way. To put that in relation to what came before, the Great Attractor lies roughly 200 to 250 million light-years away. The Shapley concentration is more than 4 times farther. At that distance, in the middle of the 20th century, a precise measurement of its mass and gravitational influence was simply beyond the capabilities available. The surveys that would have been needed did not exist yet. As instrumentation improved through the late 20th century, the picture began to fill in. The Shapley concentration was not a single galaxy cluster, it was a supercluster, a collection of galaxy clusters bound together into a larger structure. Modern surveys have identified it as containing more than 8,000 individual catalogued galaxies, organized into dozens of major clusters. The central cluster alone, known as Abell 3558, carries a mass comparable to the most extreme structures in the local universe. The total estimated mass of the Shapley concentration, including the invisible dark matter that makes up the majority of all cosmic mass, reaches figures on the order of 10,000 to 100,000 trillion times the mass of our star. Those are numbers so large that comparison to human-scale objects becomes meaningless. The only useful scale is cosmic. Early studies produced wildly contradictory estimates of how much Shapley's gravity was actually influencing our motion. Some calculations suggested a modest contribution. Others suggested it was the dominant factor. The disagreement persisted through the 1990s and into the 2000s because of exactly the same measurement difficulties that had inflated the Great Attractor's mass. Mapping a structure 650 million light-years away with enough precision to calculate its gravitational influence on our local neighborhood is genuinely difficult, and the uncertainties compound at every step. What became clearer over time, especially after the Great Attractor's mass was revised sharply downward in 2005, was that Shapley had to be responsible for a large portion of our peculiar velocity. The mathematics demanded it. Something had to account for the remaining 56% that the Great Attractor could not explain. The giant behind the curtain had been there the entire time, noticed by a brilliant astronomer in 1930, and only now beginning to receive its proper accounting. But to understand just how enormous our cosmic neighborhood truly is, the story needed one more revolution, and it came not from measuring where things are, but from tracking where they are going. In 2014, a paper published in the journal Nature introduced a new way of thinking about our address in the universe. The team behind it, led by astronomer Brent Tully at the University of Hawaii and including Helene Courtois, Yehuda Hoffman and Daniel Pomerade, was not simply building a bigger map of where galaxies sit in space. They were mapping where galaxies are moving. The distinction is fundamental. When you know only the positions of objects, you can describe a structure. When you know the velocities as well, you can understand the gravitational currents shaping the entire system. A galaxy is not a static dot in space. It is a point on a trajectory, moving toward regions of higher mass density and away from regions of lower density. If you can measure thousands of those trajectories simultaneously, you can trace the underlying gravitational landscape that drives them, the way you can infer the shape of a riverbed by watching where the water flows. The team used a technique called peculiar velocity mapping. For thousands of galaxies out to roughly 500 million light-years, they measured the deviation of each galaxy's velocity from what pure cosmic expansion would produce. That deviation reveals local gravitational influence. A galaxy moving faster toward you than expansion predicts is being pulled in your direction by some nearby mass. A galaxy moving slower is being pulled the other way. From these thousands of individual measurements, the team constructed a three-dimensional flow field, a map of which direction every galaxy in the sampled volume was moving and how fast. They then looked for the edges of this flow. Where did the galaxies on one side flow toward a different attractor than the galaxies on the other side? Those dividing lines, like watershed boundaries between river drainage basins, defined the edges of a supercluster. What they found was a structure 520 million light-years across, containing approximately 100,000 galaxies, with a total gravitating mass estimated at 100,000 trillion times the mass of our star. They named it Laniakea. The word is Hawaiian, drawn from a traditional creation chant, and it means immense heaven or immeasurable heaven. The name was suggested by a Hawaiian language expert named Nawa'a Napoleon, and it fits. The thing it names is genuinely beyond ordinary spatial imagination. Inside Laniakea, every galaxy flows toward a single region, the great attractor at the structure's center. From the opposite side of this 500 million light-year expanse, galaxies are drawn inward. Our own galaxy, our entire local neighborhood, is caught in that flow, carried along like everything else, toward the central concentration. The visualization that accompanied the paper became one of the most watched astronomy videos in internet history. It showed, for the first time, exactly what our cosmic watershed looks like from outside. A vast, irregularly shaped cloud of flowing matter, with tendrils curling inward and a center of convergence at the heart. It was the most precise map of our cosmic home ever produced. And within months, astronomers began asking whether Laniakea itself was the whole story. The Milky Way does not sit at the center of Laniakea. It sits near the outer edge, in a region of the supercluster's structure that is relatively sparse and unpopulated compared to the dense heart. To use a human-scale analogy that may help, if Laniakea were a great metropolitan region, our galaxy would be a small town on the distant fringe, not the downtown, and not even close to it. That edge position matters for what comes next. All the galaxies within Laniakea, regardless of where they sit within the structure, flow toward the great attractor at its center. The flow lines drawn by Tully's team show this convergence clearly, motion from all directions pointing inward, like tributaries feeding a central river. Our galaxy is part of that inflow, carried along by the same gravitational pull that draws everything in Laniakea toward the Norma cluster region. But Laniakea is not gravitationally bound. This is an important distinction, confirmed by the same data that defined the supercluster in the first place. A gravitationally bound structure is one where the mutual gravity of the members is strong enough to overcome the expansion of the universe and eventually pull everything together. Galaxy clusters are bound. Groups of galaxies are bound. Our local group of galaxies, which includes the Milky Way and Andromeda and dozens of smaller companions, is gravitationally bound. These smaller structures will stay together and eventually merge. Laniakea as a whole will not. The universe's expansion is stretching the structure apart faster than the gravity within it can hold it together. Laniakea is defined by a common flow pattern right now, in this cosmic moment, but it is not a permanent object. Over billions of years, its outer regions will disperse. The name remains appropriate anyway. The immense heaven is real, even if it is temporary on cosmic timescales. What makes this chapter end on something genuinely unsettling is what the next generation of surveys began to reveal. In 2024, a team using the Cosmic Flows 4 catalog, a database of more than 56,000 measured galaxy distances, published a new analysis of gravitational flow basins. They found that the boundary of Laniakea may not be where the 2014 paper placed it. The flows, traced outward, appeared to continue beyond Laniakea's defined edge. Galaxy motion that should, by the 2014 model, be flowing towards some other attractor was instead still pointing toward the same general region. The implication was striking. Laniakea might itself be embedded within a larger basin of attraction, centered on the Shapley concentration. If that analysis is correct, and the team placed the probability at 60%, then our cosmic address is not Laniakea. Laniakea is a suburb. The actual basin we belong to could be 10 times larger in volume, with the Shapley concentration at its gravitational heart. The immense heaven turns out to be the front yard of something even more immense, and that something, we now know, is only part of the picture. Because while astronomers were mapping what pulls us forward, another discovery was being made about what pushes us from behind. Everything we had discovered so far pointed in one direction: pull, dense clusters tugging at our galaxy through the dark. The Great Attractor, the Shapley Supercluster, a gravitational landscape dominated by enormous overdensities demanding that matter fall toward them. But the numbers never quite worked. Even after accounting for the combined mass of the Great Attractor and Shapley together, the full peculiar velocity of our galaxy still could not be explained. Researchers kept running the math and arriving at the same uncomfortable conclusion. Something else was contributing, something they had not yet mapped. The answer came in January 2017, from the same team that had named Laniakea. Yehuda Hoffman, Daniel Pomered, Brent Tully, and Hélène Courtois published a paper in Nature Astronomy revealing a vast supervoid in the opposite direction from Shapley. They named it the Dipole Repeller. Here is what makes this strange. Voids do not push. There is no mechanism in standard physics for empty space to generate outward force. What actually happens is subtler and in some ways more unsettling. Imagine standing on a hillside that slopes steeply in one direction and gently in another. You roll downhill toward the steep slope. From your perspective, the gentle slope behind you appears to be pushing you away. It is not. It simply has less gravitational pull than the steep side. The imbalance is what drives your motion. That is the dipole repeller. A region of space so empty, so lacking in mass, that everything around it accelerates away from it relative to what it would do in a perfectly uniform universe. The void extends across more than 1 billion light-years. To give that scale a shape, if you place this void next to Laniakea, it would be nearly twice as wide as our entire home supercluster. Inside that billion light-year expanse, there are essentially no galaxies. The cosmic web, which elsewhere fills the universe with filaments and nodes and clusters, simply goes quiet. Matter followed the attractors long ago, drained away from this region like water flowing from a dry plateau, leaving behind an emptiness so complete that astronomers can barely find objects to catalogue. What confirmed all of this was the velocity flow field. Tully's team used surveys of galaxy motions to reconstruct the gravitational landscape in 3 dimensions. When they subtracted the Hubble flow, what remained was a picture of every galaxy in our neighborhood being pushed away from one void and pulled toward one supercluster at the same time. 2 forces, 1 motion. This finding had an immediate consequence that nobody expected. The dipole repeller and the Shapley concentration turned out to contribute approximately equally to our galaxy's peculiar velocity, roughly 50% each. The Great Attractor, The structure that began this entire story was already a smaller player than Shapley. Now, Shapley itself was sharing the stage with an absence of matter rather than a presence of it. The void turned out to be just as powerful as the mountain. For the first time, the full picture of our motion through the cosmos was becoming coherent. A push from behind, a pull from ahead, a gravitational landscape shaped by both what exists and what does not. But here is what nobody had fully explained yet. How do we actually measure all of this? What is the cosmic instrument that makes our speed undeniable? The answer has been visible since the Big Bang itself, and it covers the entire sky. Think of the universe as terrain. Dense clusters of galaxies are the valleys, low points in the gravitational landscape, where matter collects and flows accelerate. Vast supervoids are the plateaus, regions so underdense that everything in their vicinity rolls away from them and downhill toward denser ground. Galaxies, galaxy clusters, superclusters, even our entire local group, are all water on this landscape, flowing along the contours of a geometry that has been building since the first seconds of existence. Now picture where our galaxy sits. Ahead of us, at a distance of roughly 650 million light-years in the direction of the constellation Centaurus, lies the Shapley Supercluster. It is the deepest gravitational valley in our local universe. Thousands of galaxies clustered into a region of space so dense that it bends the flow field of everything within reach. Its total gravitating mass, once dark matter is included, may rival 10 quadrillion times the mass of our star. Behind us, 2 billion light-years away, lies the Dipole Repeller, an expanse of near emptiness that stretches over 1 billion light-years in diameter. No significant clusters, no massive filaments, just the background hum of scattered matter left behind when everything else drained away toward denser regions long ago. Together, these two structures explain something astronomers struggled with for decades. The Great Attractor region, the structure that dominated this story for 30 years, actually accounts for only 44% of our galaxy's peculiar velocity. Shapley does more. The Dipole Repeller does just as much as Shapley. Add the two together, and the equations finally close. This is a confirmed result. The 2017 paper by Hoffman, Pomered, Tully, and Courtois established it through three-dimensional velocity field reconstruction, using observations of thousands of galaxies. It is one of the most thoroughly verified findings in large-scale structure cosmology. What it means in practical terms is this. Our galaxy is not simply being attracted by something, it is being channeled. Like water running through a landscape shaped by both mountains and valleys, our motion is the product of simultaneous forces pulling from one direction and releasing from another. You cannot understand why we move by looking only at the attractors. The voids matter just as much. There is something philosophically striking about this. For most of the history of observational cosmology, the field focused on finding things. Galaxies, clusters, superclusters, structures. The breakthrough that finally explained our motion came from mapping nothing, from recognizing that an absence of galaxies over 1 billion light-years was itself a gravitational object capable of shaping the universe's flow field. The Dipole Repeller was invisible in the old way of thinking about structure. You cannot photograph emptiness. You cannot catalog voids the way you catalog clusters. What revealed it was the behavior of matter around it, the way galaxies moved in its vicinity, tilting always slightly away, like compass needles deflecting from a field they cannot see. Now, both sides of the equation are known: the pull, the push, the full gravitational landscape in which our galaxy has been traveling for billions of years. But there is a separate question, a deeper one. How fast are we actually moving through all of this? The attractors and repellers explain the direction. What measures the speed with absolute certainty? The answer requires turning away from galaxies entirely and looking at the oldest light in the universe. In 1965, two radio engineers named Arno Penzias and Robert Wilson were trying to eliminate noise from a communications antenna in New Jersey. No matter what they did, a faint hiss remained. It came from every direction equally. They checked everything. They even cleaned bird droppings from the antenna dish, assuming contamination. The noise refused to go away. What they had accidentally discovered was the cosmic microwave background. The thermal afterglow of the Big Bang itself, still filling every cubic centimeter of space, cooled over 13.8 billion years to just 2.7 degrees above absolute zero. The universe's oldest light imprinted on the sky in every direction at once. At first it appeared perfectly uniform. The temperature in every direction seemed identical to extraordinary precision. Then cosmologist Dennis Sciama noted in 1966 that it could not truly be uniform. If we are moving, the background radiation ahead of us should appear slightly hotter and the background behind us slightly cooler due to the Doppler effect. The same way a siren sounds higher pitched as it approaches you and lower pitched as it retreats. Measurements confirmed this almost immediately. The cosmic microwave background is not perfectly uniform. One side of the sky is warmer than the other by approximately 3 millikelvin, 0.003 of a single degree. That difference is real, consistent, confirmed by every major satellite mission over the past 4 decades. The COBE satellite confirmed it. The Wilkinson Microwave Anisotropy Probe refined it. The Planck satellite measured it to extraordinary precision in 2018. Our solar system moves at approximately 370 kilometers per second relative to the cosmic microwave background radiation. That translates to roughly 828,000 miles per hour. Pause on that. A direct, absolute measurement of our speed through the universe, derived from a temperature difference of 0.003 of a degree in the oldest light we can observe. This is not a model. It is not an estimate derived from galaxy catalogs or distance measurements. It is a direct observation, but there is a subtlety. That number, 370 kilometers per second, is the speed of our solar system. Our galaxy as a whole moves faster at approximately 627 kilometers per second relative to the cosmic microwave background, once the orbital speed of our solar system around the galactic center is properly accounted for. The difference between those two numbers, roughly 260 kilometers per second, represents the stacked motions of our solar system around the galaxy and the galaxy within the local group. 627 kilometers per second, over 1,300,000 miles per hour. This is the peculiar velocity of a region of space roughly 1 million light-years across, moving together toward the great Attractor and Shapley like a continent drifting. And this measurement poses a strange puzzle that remains unresolved. When astronomers count radio galaxies distributed across hundreds of thousands of light-years, they detect a pattern in the sky that should match the cosmic microwave background dipole in both direction and amplitude. It does not match. Multiple independent surveys find the radio dipole is 2 to 4 times larger than the cosmic microwave background dipole predicts. This discrepancy has been confirmed by at least 4 separate datasets as of 2025, and nobody has a satisfying explanation for it. The speedometer is working, the reading is undeniable. What it might mean about the largest scales of the universe is something else entirely. Now it is time to add everything up. Each layer of motion we have described is real. Each is confirmed by independent measurements. Each operates simultaneously, right now, on every object sitting on this planet. When you layer them all together, the total is a number so large that the mind struggles to find something to compare it to. Earth rotates at roughly 1,040 miles per hour at the equator. You feel nothing. Earth orbits our star at approximately 67,000 miles per hour. It covers about 1.6 million miles every single day. In the time it takes to read a single sentence aloud, you have moved almost 12,000 miles around the orbit. You feel nothing. Our solar system orbits the center of the Milky Way at somewhere between 496,000 and 560,000 miles per hour. One complete circuit takes approximately 220 million years. The last time our solar system occupied this exact position in the galaxy There were no dinosaurs, no mammals, no complex animals of any kind on Earth. We have completed roughly 20 of these orbits in Earth's entire history. You feel nothing. Our galaxy moves through the local group. The local group falls toward the Virgo cluster. All of that contributes roughly 260,000 additional miles per hour when referenced against the cosmic microwave background. And then there is the peculiar velocity of our entire region of the cosmos, over 1,300,000 miles per hour, channeled by the Dipole Repeller and the Shapley Supercluster in a flow that encompasses millions of light-years of space moving together. Add it all together, Earth is currently traveling at well over 1.9 million miles per hour through the universe. Not 1 million, not 500,000, 1.9 million miles per hour. That is approximately 2,500 times faster than the speed of a bullet fired from a rifle. You feel none of it. The reason is one of the most elegant facts in all of physics. There is no friction in space. There is no medium to push against. Every inertial reference frame is equally valid, meaning there is no experiment you can perform inside a smoothly moving environment to detect that movement. We are passengers on a vessel that has never decelerated, never changed surface conditions, never given our bodies any signal that anything unusual is happening. We are, to use the phrase precisely, fish who have never seen water. The medium we move through is space-time itself, and the velocity is encoded only in that faint 3 millikelvin warmth on one side of the sky. This is not merely abstract, it is the physical reality of every human who has ever lived. The ancient astronomers who mapped the stars, the sailors who navigated by them, the philosophers who argued about whether Earth moved at all. Every one of them was hurtling through the cosmos at nearly 2 million miles per hour, completely unaware. But as remarkable as this total is, the story ahead becomes stranger, because not everyone agreed that this motion was what it appeared to be. Some astronomers looked at all of this and asked a very different question. What if the numbers themselves were built on a mistake? Science is a machine for finding errors. Sometimes the error is in the theory, sometimes it is in the observation, and sometimes it is in the mathematics that connects them. When the Seven Samurai published their findings in 1987, they had done something technically demanding, measuring the peculiar velocities of elliptical galaxies by comparing their observed properties to a relationship between size, brightness, and rotation speed called the fundamental plane. It was meticulous work. It was also work built on a chain of assumptions, each one introducing a small uncertainty, each uncertainty multiplying against the next. The problem that would haunt the field for 2 decades already had a name. It was called the Malmquist bias. Here is how it works. When you observe galaxies at increasing distances, you can only detect the brightest ones. The faint, dim members of any distant population fall below the threshold of your instruments. This means your sample at large distances is systematically skewed toward intrinsically luminous objects. And if you are using brightness to infer distance, as the fundamental plane method effectively does, that skew introduces a systematic error. Distant galaxy populations appear slightly closer than they really are. Closer populations appear to have systematically higher velocities. The result, when you do not correct for this effect, is a pattern in the data that looks exactly like coherent gravitational streaming toward a central attractor, an artifact that mimics a physical signal. This was not a fringe concern. A series of papers in the 1990s and early 2000s examined the Great Attractor evidence carefully and concluded that Malmquist bias had inflated the original mass estimates dramatically. The 2005 clusters in the Zone of Avoidance survey reduced the Great Attractor's estimated mass by roughly 90%. Let that land. For nearly 20 years, the textbook description of our cosmic neighborhood featured a structure 10 times more massive than it actually was. Every popular article, every documentary, every astronomy lecture that described the Great Attractor was describing something that did not exist in the form it was being presented. The confirmed finding, as of today, is this. The Norma cluster at the Great Attractor's heart is a real and massive structure. The streaming motion toward it is real. The peculiar velocity of our galaxy is real. What was wrong was the inferred mass, and consequently, the assumption that it alone could account for our motion. The skeptical challenge runs deeper than just mass estimates, though. Early peculiar velocity surveys relied on galaxy distances that carried uncertainties of 15 to 20%. That sounds manageable until you realize that the signal they were trying to detect, the coherent streaming motion, was itself only a few percent deviation from the Hubble flow. A 15% uncertainty in the measuring stick means the quantity being measured is swamped by noise. Some researchers in the early 2000s argued that statistical artifacts in the distance data could generate apparent streaming motions that had no physical reality at all. The data on this reading was not measuring the universe, it was measuring its own limitations. The response from the mainstream community was to build better surveys, larger samples, more distance indicators, three-dimensional flow maps instead of one-dimensional velocity plots. They answered the skeptics with more data, and the motion remained. But the skeptical instinct was correct about one thing. Some of the most dramatic claims in this field, the ones that generated the biggest headlines, would eventually fall apart under scrutiny. What comes next is the most controversial discovery in modern cosmology. In 2008, a physicist named Alexander Kashlinsky sat down to write a paper he knew would cause trouble. Kashlinsky worked at the Goddard Space Flight Center, and he had spent years developing a technique for extracting a faint signal from the cosmic microwave background. The technique exploited something called the kinematic Sunyaev-Zeldovich effect. It works like this. When light from the cosmic microwave background passes through a galaxy cluster, the hot gas inside the cluster scatters some of that light. If the cluster is moving toward us, the scattered photons get slightly blue shifted. If the cluster is moving away, they get slightly red shifted. The effect is extraordinarily small, less than 1/10 the strength of the thermal signal from the cluster itself. But if you study hundreds of clusters simultaneously and average the signal carefully, the noise averages away and the motion signal survives. Kashlinsky and his collaborators studied approximately 700 galaxy clusters using data from the Wilkinson Microwave Anisotropy Probe satellite. What they found was this: all 700 clusters were moving coherently in the same direction. The flow persisted across every distance they could measure. The clusters were not scattering randomly the way the standard model predicted. They were streaming as a coordinated group toward a specific point in the sky. The velocity was nearly 2 million miles per hour. The flow extended to at least 2.5 billion light years. Kashlinsky called it dark flow. The name would stick, and the controversy around it would not let go for years. The word dark here does not mean dark matter or dark energy. It means invisible, unaccounted for, unexplained. A flow with no visible cause anywhere within the observable universe. Kashlinsky told journalists they had never set out to find this signal and could not make it disappear no matter how they approached the data. In a follow-up study 2 years later, his team expanded the cluster catalogue to roughly 1,400 objects. The signal remained. The flow maintained approximately the same velocity at distances twice as large as the original detection. The direction pointed toward a broad patch of sky between the constellations Centaurus and Vela. If dark flow is real, it is among the most significant observational discoveries in the history of cosmology. Standard cosmological models predict that, on scales larger than roughly a few hundred million light-years, the universe should look statistically the same in all directions. Any bulk flows should cancel out. There should be no preferred direction. A coherent motion extending across 2.5 billion light-years violates this prediction completely, and the only mechanism that could produce such a flow is something extraordinary. To pull on matter across distances that large, across the entire observable universe, if the signal truly extends that far, there would need to be gravitational sources that our telescopes cannot see because they lie beyond the cosmic horizon, beyond the edge of everything we can ever observe. Kashlinsky's team proposed that the dark flow might be evidence of massive structures that formed before or during the period of cosmic inflation, structures that now lie outside the bubble of space from which light has had time to reach us. In other words, evidence of something beyond our universe. That claim would not go unchallenged. To understand why dark flow caused such a crisis in cosmology, you need to understand the principle it threatened. The cosmological principle is one of the foundational assumptions of modern cosmology. It states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means the same everywhere. Isotropic means the same in every direction. There is no special location. There is no preferred direction. Matter, on average, is distributed uniformly across the cosmos, and the expansion of space proceeds equally in all directions. This principle is not merely a theoretical preference, it is what makes the standard cosmological model work. Without it, the equations that describe the universe's evolution become vastly more complicated, potentially unsolvable without knowledge of initial conditions we cannot access. The cosmological principle is a working assumption that has been tested repeatedly and has held up well for most purposes. Dark flow, if real, breaks it entirely. A coherent motion of galaxy clusters across 2.5 billion light-years means there is a preferred direction in the universe. A direction, a special axis in a cosmos that foundational theory insists has none. Something is pulling on matter from a distance so vast that it cannot be within our observable horizon. Standard structure formation, the gravity of galaxies and clusters and superclusters, accumulating over billions of years, cannot produce a bulk flow that coherent across that scale. The theoretical maximum for a gravitationally induced bulk flow of this kind, based on standard models, is much smaller in both velocity and spatial extent. The only physical mechanism that could explain what Kashlinski observed is something that formed before or during inflation, something that now sits beyond the boundary from which light can reach us in the age of the universe so far. The universe we can observe, the sphere of space roughly 93 billion light-years across, is not the entire universe. Standard inflation predicts that the full universe is many orders of magnitude larger. If matter beyond our horizon is not distributed uniformly, it would exert gravitational pull on our side of the boundary. Pull that we might be able to detect as a bulk flow. Pull exactly like what Kashlinski claimed to have measured. The implications are radical. If structures beyond our horizon are pulling on us, those structures could themselves be other regions of the universe that experience different histories during or after inflation. In some theoretical frameworks, inflation produces a universe of distinct bubbles, each with its own local physics and initial conditions. Neighboring bubbles, if they exist close enough to our horizon, would exert gravitational tidal forces that could in principle produce observable effects. Dark flow, in this interpretation, would be the first observational evidence of cosmological structure beyond the edge of the known universe. Kashlinski was careful about this. He stated the observation clearly and presented the multiverse interpretation as one possibility among others, not a conclusion. The confirmed claim was the bulk flow itself. The theoretical implications were openly speculative, but the astronomical community paid close attention. The kinematic Sunyaev-Zeldovich method was sound in principle. The cluster sample was large. The direction and magnitude appeared consistent across independent data cuts. And then the most precise satellite ever built turned its instruments toward the same clusters. What it found did not match. The Planck satellite launched in 2009 and spent 4 years mapping the cosmic microwave background with a precision no previous instrument had achieved. Its detectors could measure temperature differences of millionths of a degree. Its angular resolution was sharper than any prior mission. If any signal related to dark flow was real and anywhere near the amplitude Kashlinski claimed, Planck should have found it. In 2013, the Planck collaboration released its reconstruction of galaxy cluster velocities using the same kinematic Sunyaev-Zeldovich method Kashlinski had employed. Their conclusion was measured but clear. They found no statistically significant dark flow at the amplitude reported in the 2008 paper. The velocity signal in their data was consistent with zero. This was a significant challenge. The kinematic Sunyaev-Zeldovich effect is among the most technically difficult signals to extract from cosmic microwave background data, The thermal signal from the cluster gas is many times stronger than the kinematic component. Separating them requires precise knowledge of each cluster's temperature structure, detailed modeling of foreground contamination, and careful statistical treatment of a sample that inevitably contains measurement scatter. Critics of Kashlinsky's work pointed to several sources of potential systematic error. The cluster sample used in the original study was drawn from X-ray catalogs that had their own selection biases. The signal-to-noise ratio for any individual cluster was well below detectability. The claimed detection depended entirely on statistical averaging. Small errors in the foreground model, the kind that accumulate quietly in any large-scale analysis, could produce apparent correlations that looked like coherent motion. Fernando Atrio Barandella, one of Kashlinsky's close collaborators, published a reanalysis in 2015, arguing that the Planck data, when properly processed, was actually consistent with the Wilkinson microwave anisotropy probe findings that had produced the original detection. The debate became highly technical, with competing teams disputing the methodology of each other's analyses at a level of detail accessible only to specialists. Multiple follow-up studies produced genuinely conflicting results. Some confirmed a bulk flow in roughly the expected direction. Some found signals consistent with zero. Some found signals smaller than Kashlinsky's original estimate but larger than Planck's upper limit. The field fractured along methodological lines, with researchers disagreeing about how to handle systematic errors before they could agree about what the data said. This is science operating at its edge. That phrase is often used as a comfortable softening of "we do not know." Here it means something more specific. The measurement in question is so close to the noise floor of current instruments that distinguishing a real signal from a systematic artifact requires assumptions, and the results depend heavily on which assumptions you make. What is confirmed, bulk flows on scales up to a few 100 million light-years are real and well established. What is uncertain? Whether the flow extends coherently out to 2.5 billion light-years. What is genuinely unknown? Whether the signal Kashlinsky measured represents physical reality or accumulated systematic error. As of 2026, the dark flow question remains open. The Euclid Space Telescope, launched in 2023, is expected to provide a definitive answer using an independent approach. But while that debate continued, a different kind of cosmic discovery arrived from an entirely unexpected direction. A sphere of galaxies, 1 billion light-years across, sitting in our cosmic backyard. In September 2023, Brent Tully sat down to write a paper about a discovery so improbable that his team spent months verifying it before publishing. Using the Cosmic Flows 4 catalog, a compilation of distance measurements for over 56,000 galaxies assembled by Tully's group at the University of Hawaii over years of work with the Hubble Space Telescope and several other observatories, the team had identified something in the data that had never been seen before: a spherical shell of galaxies, 1 billion light-years in diameter, located 820 million light-years from the Milky Way. They called it Ho'olelana, a name drawn from the Kumulipo, the Hawaiian creation chant, meaning "sent murmurs of awakening." The structure is extraordinary on multiple levels. First, its scale, 1 billion light-years across. Our entire home supercluster, Laniakea, spans 520 million light-years. Ho'olelana is nearly twice that size. It contains within its shell the Sloan Great Wall, the Harvard-Smithsonian Center for Astrophysics Great Wall, and the Hercules Supercluster Complex. The Boötes Supercluster sits at its geometric center. Inside the shell, there is the Boötes Void, one of the largest known empty regions in the observable universe. Second, its proposed identity. Tully's team believed they had found the first individual baryon acoustic oscillation ever resolved as a distinct physical structure. A baryon acoustic oscillation is a fossilized sound wave. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma. Sound waves, pressure oscillations, propagated through this plasma at about 58% the speed of light. When the universe finally cooled enough for hydrogen atoms to form and light to travel freely, these waves froze in place. They stopped propagating and left their imprint on the distribution of matter throughout the cosmos. The scale of a frozen baryon acoustic oscillation is fixed by the speed of sound in the early universe and the moment at which the plasma cooled. It corresponds to a characteristic separation of roughly 500 million light-years. When astronomers study the statistical distribution of galaxy separations across large surveys, they find a slight excess of galaxy pairs at this scale. That excess is the baryon acoustic oscillation signal, confirmed in hundreds of statistical analyses over 2 decades. But those are statistical patterns across millions of galaxies. Nobody expected to find one as a single, identifiable sphere in the sky. Ho'olelana appears to be exactly that. This is described by the research team as a probable identification, not an absolute certainty. The structure's geometry is consistent with a baryon acoustic oscillation. Its diameter matches the predicted scale. Its shell contains the kind of overdensity expected from a frozen pressure wave. The team is confident enough to publish, but careful to note that a single structure cannot be definitively identified as a baryon acoustic oscillation without the statistical context that comes from finding many such spheres. If it is what they think it is, we live inside an echo of the Big Bang, and the implications for our measurement of the universe's expansion rate were even more startling than the discovery itself. The baryon acoustic oscillation is one of cosmology's most powerful tools. Here is why. Because the scale of the frozen sound wave is set by physics in the early universe, a physics we understand well, it provides a standard ruler, a length we can predict from first principles. If we observe that ruler in the galaxy distribution today and measure how large it appears on the sky, we can calculate how far away that region of the universe is. If we then measure its redshift, how much the universe has stretched since that light was emitted, we can calculate the rate of expansion. This is how baryon acoustic oscillations became one of the primary methods for measuring the Hubble constant, the number that describes how fast the universe is currently expanding. The problem is that 2 completely different methods of measuring the Hubble constant have been giving different answers for over a decade. Measurements based on the cosmic microwave background and the standard cosmological model give a value of approximately 67 kilometers per second per million light-years. Direct measurements based on nearby distance indicators, including Type Ia supernovae and Cepheid variable stars, consistently give values around 73 kilometers per second per million light-years. The gap between these 2 numbers is statistically significant. It persists across multiple independent datasets and multiple independent teams. Cosmologists call it the Hubble tension. Now, Ho'olelana entered the picture. If the sphere is a genuine baryon acoustic oscillation, its observed diameter gives an independent measurement of the Hubble constant. Thuley's team carried out that calculation. Their result, 76.9 kilometers per second per million light-years. Not 67, not 73, 76.9, higher than both of the values in the existing debate. This result is preliminary. It comes from a single structure, a sample size of 1, in a field where robust measurements require many observations averaged together. The uncertainty range in Thuley's calculation is large enough to be consistent with the higher end of existing measurements, though not with the cosmic microwave background value. It should be treated as a data point, not a conclusion. What it represents, though, is this. If the universe is genuinely full of these fossilized acoustic shells, and we are only beginning to resolve individual ones because our surveys are finally large enough and precise enough to see them, then each new identification adds to our understanding of how matter is distributed across the cosmos and how fast space is expanding. We live inside one of these shells. The Milky Way sits within Ho'olelana's volume, closer to the outer edge than to the center. When you look out at the large-scale structure of our cosmic neighborhood, some of what you are seeing, the arrangement of superclusters and voids that surrounds us, reflects the geometry of a sound wave that propagated through the plasma of the newborn universe before any star had yet ignited. The echo has been around us all along, and far beyond our neighborhood, at distances 9 billion light-years away, two other structures have just been discovered that should not exist by any physics currently understood. They are larger than the theory allows, and they are sitting almost side by side in the sky. A graduate student found something that should not exist, and the field of cosmology has been struggling to explain it ever since. Alexia Lopez was working on her doctorate at the University of Central Lancashire when she spotted a pattern in data collected by the Sloan Digital Sky Survey. She was studying the way ancient quasar light picks up chemical fingerprints as it crosses the universe. When that light passes through the gas halos surrounding galaxies and clusters, it collects absorption signatures, like a traveler whose coat carries the smell of every town they passed through. By reading those signatures across tens of thousands of sightlines, Lopez could map the matter lying between us and the most distant light sources in the sky. In 2021, she announced a finding that stopped astronomers mid-sentence. The structure she had mapped was a vast, curving arc of galaxies and galaxy clusters stretching 3.3 billion light-years from end to end. It hung in the sky near the constellation Boötes, 9.2 billion light-years from Earth. The light revealing it left its source before our planet formed. Here is the problem. According to the cosmological principle, and every major simulation astronomers have built to model the universe, the largest coherent structure that gravity and expansion should allow is roughly 1.2 billion light-years across. The giant arc is nearly 3 times that limit. When scientists first heard the announcement, the argument started almost immediately. Then Lopez went back to work. In January 2024, at the 243rd American Astronomical Society meeting, she announced a second discovery at almost exactly the same cosmic distance and only 12 angular degrees away from the giant arc in the sky. She called it the Big Ring. The Big Ring measures 1.3 billion light-years in diameter. Its full circumference reaches 4 billion light-years. If it were somehow visible from Earth with the naked eye, its disk would span the width of 15 full moons placed side by side across the night sky. And it sits at the same cosmic epoch as the giant arc, two enormous structures in the same era and the same region of the heavens. The Big Ring carries an additional surprise. When Lopez's team examined its geometry carefully, they found it is not a flat circle. It corkscrews through space in a corkscrew spiral, its plane facing almost directly toward Earth, meaning we are looking at it nearly head-on. Neither structure fits neatly into any accepted explanation. Baryon acoustic oscillations, the fossilized pressure waves from the earliest universe, carry a characteristic scale of roughly 500 million light-years. The Big Ring is more than twice that size, and its geometry is wrong for a sound wave remnant. Cosmic strings, topological defects left over from phase transitions in the early universe, have been proposed as a possibility. Physicist Roger Penrose's conformal cyclic cosmology raises the idea that rings like these could be echoes from the collision of black holes in a universe that existed before our own Big Bang. Oxford physicist Subir Sarkar said it plainly. The rings change the game altogether, and that is nothing you would expect to find by chance. Lopez has since reported an even larger outer arc partially encircling both structures. The picture keeps growing, and what it is growing into puts one of the most fundamental pillars of modern cosmology under enormous pressure. The cosmological principle is not a minor working assumption. It is the bedrock on which every cosmological model of the last century has been built. The principle states, at its core, that the universe is homogeneous and isotropic on large enough scales. Homogeneous means the same everywhere. Isotropic means the same in every direction. Together, they allow scientists to write equations that describe the entire observable universe as a single system. Without that assumption, the mathematics of cosmology as we know it would collapse. There would be no single Hubble constant, no uniform rate of expansion, no universal description of dark energy. The principle has been confirmed repeatedly at moderate scales. Surveys of millions of galaxies show that the universe, averaged over volumes of a few hundred million light-years, does look statistically smooth. Dense filaments and voids average out when you zoom far enough back. The question is how far back is far enough? The theoretical upper limit for a coherent structure, the largest thing gravity and expansion should be able to maintain before the universe's smoothness overwhelms local clustering, sits at around 1.2 billion light-years. This number flows directly from the cosmological principle. Structures larger than this are, in the language of physics, forbidden. The giant arc is 3.3 billion light-years across. The Big Ring spans over 1 billion light-years in diameter and 4 billion light-years in circumference. The Ho'olelana bubble identified in 2023 is 1 billion light-years wide. And in 2022, astronomers confirmed the giant gamma-ray burst ring, another circular structure measuring over 5 billion light-years across. Each one, individually, is an anomaly. Together they form a pattern. Scientists are actively debating what that pattern means. One confirmed possibility is measurement error. These are subtle signals extracted from statistical analysis of millions of faint objects across cosmological distances. Systematic biases in the data could mimic coherent structure where none truly exists. This is a real concern. The history of cosmology is full of phantom structures that dissolved when better data arrived. A second possibility, currently described as a credible theory by several researchers, is that these are genuine physical structures whose existence requires new physics. Cosmic strings are one candidate. These are theoretical one-dimensional defects in space-time that would have formed during phase transitions in the early universe, similar to the cracks that form in ice when water freezes. A cosmic string could seed a ring-shaped distribution of galaxies by gravitationally focusing matter around it. A third possibility, described by physicist Roger Penrose as a specific prediction of his conformal cyclic cosmology model, is that large rings could be Hawking points, imprints of black hole evaporation from a previous cycle of the universe. This remains speculative. The most unsettling possibility is this: the cosmological principle itself may hold only within a certain range, and the universe, at scales of several billion light-years, may be genuinely inhomogeneous in ways the standard model does not permit. For now, this is an open scientific question, not a confirmed crisis. But the accumulation of anomalies is accelerating, and the instruments mapping the sky are improving every year. What changed in 2024 was not one new structure, it was a new map of everything. At the end of 2024, a paper arrived in the journal Nature Astronomy that quietly rewrote our cosmic address. The team was led by Aurélien Valade and included Yehuda Hoffman, Noam Libeskind, and others who had spent years building the most detailed three-dimensional map of galaxy motion ever assembled. Their raw material was the Cosmic Flows 4 catalog, the work of R. Brent Tully's group at the University of Hawaii, which had painstakingly measured distances to 56,000 galaxies. With those distances and velocities in hand, the team could map not just where galaxies are, but which gravitational basins they are falling into. The method is the same one that gave us Laniakea in 2014, tracing the cosmic watersheds. Just as every drop of rain on a mountain eventually reaches one ocean or another depending on which side of the divide it falls, every galaxy is flowing toward one gravitational basin or another. The boundaries between those basins are the true edges of superclusters. When Valade's team drew those boundaries using the richer cosmic flows 4 data, the picture that emerged was startling. Laniakea, our home supercluster, the structure that contains our galaxy near its outer edge, and that was itself a revelation when it was announced a decade ago, may be contained within something far larger. The data suggest there is a 60% probability that the Milky Way lies inside the gravitational basin of the Shapley concentration. The Shapley basin, if that interpretation holds, would be 10 times the volume of Laniakea. Think about what that means. A decade ago, Laniakea seemed like our home on the largest scale. 520 million light-years across, 100,000 galaxies, a mass of 100,000 billion suns. It felt like the end of the address. It may be a neighborhood within a much larger city. Tully has described the universe as a giant web where galaxies lie along filaments and cluster at nodes. and where matter flows within basins the way water flows within watersheds. What the 2024 map revealed is that those basins extend further than anyone had calculated. The Shapley concentration, already the most massive known concentration of matter in the local universe, may be the gravitational anchor of a domain encompassing everything we have so far mapped and more. The paper also confirmed something about the 5 additional superclusters mapped by a 2023 study from the same group. Those superclusters, named Apus, Hercules, Lepus, Perseus Pisces, and Shapley, are all significantly larger than any theoretical simulations of standard cosmology predict them to be. The discrepancy is described by the researchers as an unresolved puzzle. Our cosmic address keeps expanding. Each revision makes the next layer of structure sound familiar, and then the layer after that peels away to reveal something larger still. But there is another force shaping our journey through this structure, and it does not come from any attractor. It comes from behind us. To understand why we move, you need to understand both sides of the equation. For decades, astronomers treated the Milky Way's peculiar velocity as a story entirely about attraction. The great attractor was pulling. Then Shapley was pulling harder. The logic was gravitational, and the assumption was that all the important physics lay in the direction we were heading. The vast underdensities behind us were little more than background scenery. The 2017 discovery of the Dipole Repeller began correcting that picture. A billion light-year-wide void in the direction roughly opposite to Shapley, containing essentially no galaxies, was contributing as much to our motion as all the attractors combined. The physics was not anti-gravity, it was geometry. In a region where there is almost no matter, the gravitational pull is weaker than the cosmic average. Relative to a uniform universe, that imbalance acts like a slope that galaxies roll away from. We were not just being pulled forward, we were being pushed from behind. But the discovery in September 2017 of a second massive void, identified by the same team in the direction of the cosmic microwave background's famous cold spot, suggested the repulsive landscape behind us was even larger than anyone had calculated. The cold spot has puzzled astronomers for years. It is a region of the cosmic microwave background that is significantly cooler than the surrounding sky, an anomaly that has generated dozens of proposed explanations. A large underdensity along the line of sight can create a cool region in the background radiation through the integrated Sachs-Wolf effect, where photons lose energy as they cross a low-density region. The cold spot repeller was identified as a void whose presence contributes to this cooling. What the 2023 analysis using the cosmic flows 4 data revealed is something that changes the scale of the picture entirely. The dipole repeller and the cold spot repeller do not appear as 2 separate structures in the updated velocity maps. They appear as a single gigantic entity, a combined underdensity so large that it forms one side of the gravitational landscape defining our cosmic motion. We are caught between 2 of the most extreme features in the local universe. On one side, the Shapley concentration, the most massive known matter overdensity within a billion light-years. On the other side, a combined void system that stretches across a region large enough to dwarf entire superclusters. The repulsive side of our motion is structurally more significant than originally thought. And yet, there is something stranger still. When astronomers look at the largest scales of the universe and measure the direction our motion should produce in the background radio sky, the number they find is wrong. It is far too large, and the discrepancy cannot be explained away. Here is a prediction that should be easy to verify. If our galaxy's motion through the cosmos is caused entirely by local gravitational forces, by the pull of Shapley and the push of the dipole repeller system, then that motion should leave a specific fingerprint in the distribution of the most distant objects in the sky. Radio galaxies and quasars lie scattered billions of light-years away, far beyond the structures that influence our local motion. If we count them across the whole sky, the count should be very slightly higher in the direction we are moving toward and slightly lower behind us, because our motion compresses wavelengths slightly in one direction and stretches them in the other. This is called the radio dipole. Its amplitude and direction should match the cosmic microwave background dipole almost exactly, because both are measuring the same motion. They do not match. Multiple independent surveys have found a radio dipole that is 2 to 4 times larger than the cosmic microwave background dipole predicts. The discrepancy has been found in the NRAO VLA Sky Survey, in data from the Wide Field Infrared Survey Explorer satellite, and in the Rapid Australian Square Kilometre Array Pathfinder Continuum Survey. The direction is roughly the same as the cosmic microwave background dipole, but the amplitude is dramatically, stubbornly larger. In 2025, a team led by Burma applied the most sophisticated statistical corrections available, accounting for every known source of bias and systematic error in the surveys, and reanalyzed the data. The anomaly remained. The excess dipole signal did not shrink to the expected level no matter how carefully the noise was stripped away. What could explain this? One possibility is that something is genuinely intrinsic to the distribution of matter at the very largest scales of the observable universe. Perhaps the universe is not as homogeneous as the cosmological principle requires, even at distances of several billion light-years. The radio sources being counted are not local objects whose positions are shaped by the same gravitational flows pulling on us. They are so far away that any intrinsic clustering would have to be enormous to produce this signal. A second possibility is that our motion through space is generating effects that go beyond what standard models predict, for reasons that are not yet understood. A third possibility is systematic error at a level that has so far resisted every correction attempt. As of 2026, this is one of cosmology's sharpest unresolved tensions. It stands alongside the Hubble tension and the challenge of the giant arc as a signal that something in the standard picture may need revision at the largest scales. And then, in 2024, the instrument that measures dark energy across billions of light-years announced results that sent a shockwave through physics. For 25 years, the standard model of cosmology has rested on a single quiet assumption that the energy driving the universe's accelerating expansion is constant. Einstein introduced the idea as a mathematical term in his equations, a cosmological constant, a fixed energy density embedded in the fabric of space-time itself. He later called it his greatest mistake, but the universe turned out to need it after all. When supernova observations in 1998 revealed that the expansion of the universe was speeding up, not slowing down as gravity should cause, the cosmological constant came back as the simplest explanation for what observations were showing. Constant dark energy, eternal acceleration, a universe expanding forever into cold, empty darkness. In 2024, the Dark Energy Spectroscopic Instrument at Kitt Peak Observatory in Arizona released its first major results from a survey of 6 million galaxy redshifts. The instrument had been designed to measure the history of cosmic expansion with unprecedented precision, and the data it returned suggested that dark energy was not behaving like a constant. The signal was significant but not yet definitive. The scientific community waited. In March 2025, the instrument released 3-year results based on nearly 15 million galaxies and quasars. Combined with data from the cosmic microwave background, supernova surveys, and weak gravitational lensing observations, the evidence strengthened. When all these independent datasets were analyzed together, the best fit to the data required dark energy that evolved over time, stronger in the past, weaker today, and still weakening. The standard cosmological constant model, which assumes the ratio of dark energy's pressure to its density is exactly -1 and never changes, was rejected by the combined data with high confidence. In November 2025, a team at Yonsei University in South Korea published a corrected analysis of supernova observations in monthly notices of the Royal Astronomical Society. Their conclusion was even more direct. The universe may have already stopped accelerating. The great cosmic expansion that everyone assumed would continue forever may have entered a phase of deceleration within the last few billion years. The implications ripple through everything we thought we understood about our destination. If dark energy is weakening, the expansion that has been pushing the Shapley Supercluster away from us faster than we can approach it may be losing its strength. The attractors are not necessarily receding forever. The gravitational architecture of the cosmos may be changing, and one physicist, working with all the new data in hand, went further than anyone else dared to go in 2025. He did the calculation that most scientists had been avoiding. He calculated when the universe would end. The idea that the universe might end in collapse fell out of fashion 25 years ago. When the accelerating expansion was discovered in 1998, it seemed to seal the fate of the cosmos in cold eternity. Galaxies would drift apart, stars would burn out. Eventually, the universe would reach a state of maximum entropy, spread so thin that nothing could happen anywhere. The big freeze, the heat death, an endless, silent, empty, dark. The big crunch, the scenario in which everything eventually collapses back toward a singularity, became a historical curiosity. The textbooks moved on. In the autumn of 2025, Cornell University physicist Henry Tai published a paper in the Journal of Cosmology and Astroparticle Physics titled The Lifespan of Our Universe. Tai used the latest results from the Dark Energy Spectroscopic Instrument, from the Dark Energy Survey, and from a suite of complementary observations. He modeled dark energy as an ultralight particle called an axion, a well-motivated theoretical candidate that had been proposed decades earlier for unrelated reasons. When he fit the data, one result kept appearing regardless of how he adjusted the assumptions. The cosmological constant is likely negative. A negative cosmological constant means the energy driving expansion is not just weakening, it will eventually reverse sign. The expansion will decelerate, stop, and then turn into contraction. According to Tai's calculation, the universe will continue expanding for another 11 billion years before it reaches its maximum size. Then it will begin to contract. The collapse will accelerate as gravity compounds, and roughly 20 billion years after we reach that turning point, everything will converge back toward a singularity. Total lifespan of the universe, approximately 33 billion years. The universe is currently 13.8 billion years old. That means we are just under halfway through. Independent confirmation came in a separate paper by Shajib and Freeman, published in Physical Review D in September 2025. Their analysis of multiple dark energy datasets found that dark energy has decreased by approximately 10% in recent cosmic history, and they rejected the constant dark energy model with 99.6% confidence. The Big Crunch is no longer a discarded idea. It is a scientifically motivated possibility, supported by multiple independent lines of evidence. It is described as a credible scenario, although it remains contested, and future observations from the Euclid Space Telescope and the Vera Rubin Observatory will either sharpen or dissolve the signal in the coming years. For our story, the implications run deep. We have spent many chapters calculating the speed at which we hurtle toward the Shapley Supercluster, a destination so far away and the expansion so strong that we could never reach it. But if the expansion is truly turning around, the picture of motion without destination that seems so certain begins to change. Except for one thing. The timescales involved are beyond imagination. And what happens to the journey long before the universe ends is stranger, quieter, and in some ways more haunting. We are hurtling toward the Shapley Supercluster at over 600 kilometers per second. We have been doing so for billions of years. We will continue doing so for billions more. We will never arrive. This is the fundamental irony at the heart of our cosmic motion. Every attractor we have described in this documentary, the Great Attractor, the Shapley concentration, the entire basin of attraction that may surround them both, represents a destination we are always approaching and never reaching. The reason is dark energy. Even in its weakened form, the expansion of space continues to carry distant structures away from us. The Shapley Supercluster lies 650 million light-years away. The galaxies at its core are receding from us at a speed set by cosmic expansion, and while our peculiar velocity of 600 kilometers per second is impressive on a local scale, The recession velocity of Shapley is thousands of times larger. In the time it would take us to travel even a small fraction of the distance toward Shapley, the structure itself will have moved further away. To reach the Great Attractor region alone, traveling at our current peculiar velocity through space would take approximately 5 billion years. Our entire solar system will have changed beyond recognition long before we arrived, and the Great Attractor would itself have moved. The motion is real, the velocity is real. The destination does not exist in any practical sense. This is a condition without analogy in human experience. We move towards something that always recedes. We accelerate toward an attractor that is simultaneously being carried away by the medium we are moving through. It is not that the destination is hidden or distant in the way a horizon is distant and reachable. It is that the destination is retreating at a rate that our motion can never overcome. Think of it this way. Imagine running toward a shoreline painted on a retreating canvas. Your legs are moving, you are covering ground, but the canvas is unrolling away from you faster than your stride. You are always running, you are never arriving. Even in the scenario where dark energy eventually reverses and the universe begins to contract, the timescales involved, 11 billion years before maximum expansion, then 20 billion more years of collapse, are so vast that no meaningful sense of arrival applies. The structures we are flowing toward will have merged, dispersed, or been consumed by processes we cannot now predict. We are passengers on a journey with no station at the end, pure motion, pure becoming, a direction without a terminus. And yet there is something remarkable buried inside this fact. The scale of the motions we have described, the nested velocities, the gravitational basins, the pushing voids and pulling superclusters, are built entirely from events that happened in the first fraction of a second of the universe's existence. The architecture of where we are going is a fossil of where we came from. That realization deserves to be held carefully, because it changes what this entire journey means. Consider what has been constructed across the chapters of this documentary. At the smallest scale, Earth spins on its axis at over 1,000 miles per hour. That motion carries us around our star at 67,000 miles per hour. The entire solar system wheels around the center of our galaxy at nearly 500,000 miles per hour, completing one full orbit every 220 million years. The galaxy itself moves within the local group, which falls toward the Virgo cluster, which flows as part of Laniakea toward the Great Attractor, which is itself embedded in the larger gravitational basin of the Shapley concentration, which may be flowing within currents we have only begun to detect. Layer those speeds together, and you are moving at roughly 2 million miles per hour through the universe. You feel nothing. The attractors and repellers shaping that motion are not arbitrary. They are the direct descendants of density fluctuations that existed in the first 380,000 years after the Big Bang, when the universe was a hot plasma and pressure waves rang through it at more than half the speed of light. Those waves froze when the universe cooled and became transparent. The pattern they left behind, encoded in the distribution of galaxies across the sky, is the map of where everything is going today. We are driftwood on an ocean whose currents were carved by sound. This is confirmed by multiple independent observations. The cosmic microwave background, the distribution of galaxy clusters, the baryon acoustic oscillation pattern in large-scale surveys, the peculiar velocity fields mapped by decades of careful measurement. They all converge on the same story. The forces moving us were set in motion before any star in the universe had ignited. The Ho-Ole-Lana bubble, a billion light-year-wide spherical shell of galaxies, discovered in 2023, is a physical remnant of one of those primordial sound waves, still visible in the arrangement of matter nearly 14 billion years later. We live inside a fossil echo of the universe's first voice. Here is what makes all of this extraordinary. A creature that lives for 100 years on a world that completes one cosmic orbit every 220 million years on a speck of rock near the edge of a middling galaxy has managed to measure the curvature of the universe's gravitational landscape across hundreds of millions of light years, has found the voids pushing from behind, has mapped the basins of attraction shaping the flow of 100,000 galaxies. has traced the origin of that architecture to acoustic oscillations in a plasma that no longer exists. That achievement does not require false modesty or inflated wonder. It is simply what it is, one of the most audacious acts of knowing in the history of this planet. We do not know where we are going. The destination, as the previous chapter established, does not exist in any reachable form. But for the first time, we understand in genuine depth why we are moving, what is moving us, and how far back in time the cause of our motion reaches. That understanding is not the end of the story. The largest anomalies remain unresolved. The dipole discrepancy has no clear explanation. The giant arc and the big ring challenge the foundations of the standard model. The nature of dark energy is in active dispute. We are still inside the mystery. We have simply mapped more of its edges than anyone before us. And now, for the final accounting, let us go back to the beginning. Let us add everything up one last time. You are never still. Right now, the ground beneath you is spinning at over 1,000 miles per hour, carrying you through the arc of a single day. At the same time, this entire planet is sweeping through its orbit around our star at 67,000 miles per hour. In the 24 hours of a single day, Earth travels 1.5 million miles along that orbital path. You will never be in exactly this position again. But that orbital speed, which dwarfs any velocity a human being has ever personally achieved, is barely worth mentioning in the larger accounting. Our solar system is orbiting the center of the Milky Way at nearly 500,000 miles per hour. One full circuit takes 220 million years. The last time our solar system occupied this position in its galactic orbit, the Triassic period was beginning on Earth, and the ancestors of every dinosaur had not yet appeared. We have completed roughly 20 such orbits since our planet formed, each one a silent, unfelt revolution through a galaxy we never see from the outside. Combine those speeds, and we are already moving at more than 500,000 miles per hour, but we are not finished. The Milky Way, along with Andromeda and the dozens of smaller galaxies in our local group, is falling toward the Virgo cluster. The local group as a whole carries a peculiar velocity of over 1,300,000 miles per hour relative to the cosmic microwave background. That is the combined pull of the Great Attractor region and the Shapley Supercluster, and the push of the combined void system behind us, the Dipole Repeller and Cold Spot Repeller together forming the largest underdensity in the known local universe. Stack every layer of motion together. The final number exceeds 1.9 million miles per hour, and this is what science has assembled from decades of work across the whole breadth of astronomy. The Seven Samurai, who noticed in 1986 that something was pulling galaxies in the wrong direction. Brent Tully and Helene Courtois and Yehuda Hoffman and Daniel Pomerade, who in 2014 drew the boundaries of Laniakea and gave our home in the universe a name worthy of it. The team that found the Dipole Repeller in 2017, finally explaining why all the attractors alone were never enough. Tully and his collaborators again in 2023, identifying in Ho'olelana the first physical remnant of a Big Bang sound wave. Alexia Lopez, the graduate student who found structures 3 times larger than the universe should contain, not once, but twice, and then found something even larger encircling them both. The universe these researchers have mapped is not the one anyone expected. It is a raging river of galactic motion, shaped by forces that were set in motion before our star existed, flowing toward destinations that recede as we approach them. Structured by echoes of pressure waves from a time when the universe was smaller than the smallest star, dark energy appears to be weakening. The expansion that seemed eternal may already be slowing. A physicist at Cornell has calculated that the universe will reach its maximum size in 11 billion years, then collapse over 20 billion more years to an end. If he is right, we are traveling not only across space, but through a finite cosmic lifespan, and we happen to exist at its midpoint. The motion will continue long after everything alive on this planet is gone. The galaxies of Laniakea will keep flowing toward the Great Attractor. The Great Attractor's basin will keep flowing toward Shapley. Shapley itself will keep flowing within currents we have only begun to trace. We will not be here to watch any of it. But the fact that we looked up from this small, spinning world and measured the shape of all that motion with instruments no larger than a building and traced it backward to the first sound ever made in the universe is a thing that will stand in the record of what life on Earth once did. We are moving. We have always been moving. We are only now learning to see where.